Today we're starting chapter 12, which is all about circles. Our first section is going to be discussing tangent lines and tangent segments. Now, tangent lines and tangent segments are not going to be the same thing as that tangent trig function we talked about. They do have the same name, but they are going to be different. A tangent segment is going to be like a physical line or physical segment that is connected to a circle or a curve or some other sort of function. We're going to look at it in terms of our circles or in connection with our circles. So the definition of a tangent is a tangent line or a tangent segment is a line or a segment that just brushes up or just touches a curve or an edge. We're going to focus on circles at one point. So there's only one point in common. They don't cross through the circle. They don't hit it multiple times at just one point. So if I were to draw an example, I got my line here. It just brushes up against my edge of my circle. It doesn't cut through. We're not going through like this or anything. We're just brushing up against the edge. And then that has one point that they share in common, one point that's on the circle and the line. And we call that the point of tangency. Call that the point of tangency. All right, so that tangent line definition, that's going to lead us to our first two theorems in our chapter. No proofs at all. Remember, theorems are statements or facts that are true. And they help show different methods that we can use to solve problems or situations that would arise. Now, some of you may have printed off the chapter 12 theorem page, and so you're going to grab that, pull that out, and we're going to fill it in. We have our first two theorems here, and we're going to have an example. I'm going to try and pull it up so you can see what it looks like. So it's like this on the left-hand side if you have that. Now, not everybody has the capabilities to print or has printed that. That's fine. If you don't, I would just set aside one or two sheets of paper and create your own theorems page. All right. To get all the circles, I would get something to use as like a stencil or a guide. So typically, like if you've got like a 2-liter bottle of soda or something like that, the cap is a really good size circle that you can use to help draw all of these. But it is going to be helpful because if you notice, there's quite a few circles in here. So it would be helpful if you have that. But what we're going to do is we're going to take our two theorems we have, 12.1 and 12.2, and we're going to write them down. I've got some fill in the blanks if you have it printed off. If you don't, you just write out the whole theorem, and then we're going to draw some pictures. So I'm going to stay on the notes page. All right, but you've got your theorem page. You can fill that out. It's filled out here, so we're just going to add it in. It's sort of like how we did the passport. I had it filled out in the notes, and then you had to fill it in your passport. All right, so that first theorem, 12.1, it says if a line is tangent to a circle, then the line is perpendicular to the radius at that point of tangency. So there's going to be one example for both theorems, and I'm going to start by drawing it right now. I got that point of tangency. I got a tangent line. Remember, it's going to have one single point of tangency right there. If I were to draw in my radius, all of a sudden, you can sort of see, because it's a tangent line, that's a right angle there, and I'm going to draw a better right angle there. That's a right angle. Theorem 12.2 is the converse. It goes in the backwards direction. If a line is perpendicular to a point, perpendicular to a radius at a point on the circle, then the line is tangent to the circle at that point. So those two go together. That's only why there's one picture there. What this allows us to do is, okay, well, I could draw in another radius, and then I could continue that radius out to the edge of, say, a segment. And all of a sudden, we've created a right triangle. So we get to use everything we know about right triangles. So Pythagorean theorem, we get to use that. SOHCAHTOA, we get to use that as well. So that comes in pretty handy for us. All right, so if you need a little bit more time, you can pause the video, you can write it down. Otherwise, we're gonna move on and we're gonna do this next example here. So we've got a circle A, and point B is the point of tangency to our circle, and they give us the values of S and T. So S is 36. I'm just gonna write this over here so I can zoom in a little bit more. And then T is 48. Okay, so what we're gonna do is we are gonna solve for our radius. And because B is a point of tangency, the reason I'm allowed to draw in this right angle is because B is the point of tangency. If they didn't tell me that, then I don't know that that's a right angle. I don't know that I have a right triangle. But I do have a right triangle. Because B is my point of tangency, I have that right angle. So what I can do is I can say, well, this piece right here, this is 36. This is 48. I'm trying to find my radius. I know that both of these distances here and here are the radii, so I can call both of those R. We have a right triangle. I have an A, I have a B, and I have a C, a hypotenuse. So I can use my A squared plus B squared equals C squared. Now, notice your C is the combination of two different segments. So my C is going to be R plus 36. It is really important that you remember that R plus, that it's not just 36. Otherwise, we're going to have a slight issue there, but we're going to add those two values together. So I'm going to go back over here where I have a little bit more room to work, but I have my A squared plus B squared equals C squared. My A is R, so my radius, R squared, plus 48 squared plus equals parentheses R plus 36 squared. And we get to use those algebra skills that we've been talking about for the last couple days. Remember, when you square something, R plus 36 parentheses squared, that means R plus 36 times R plus 36. I don't get to distribute the exponent. I have to actually multiply this out. And so I can FOIL and get R squared plus 36R plus 36R plus whatever 36 times 36 is. Let's check really fast. 1,296, which gives me on the right R squared plus 72R plus 1,296. And then on the right, on the left, I have R squared plus 48 squared, which is 2,304. And we can solve for R, combine your like terms. Remember, if I got a quadratic, I want to set everything equal to 0 if possible. But notice first, if I start moving R squareds, what's going to happen with those R squareds? They're going to cancel. So we end up not having a quadratic. I get 2,304 equals 72R plus 1,296, or 72R equals 1,296 subtracted from 2,304 is 1,008. So divide both sides by 72. R equals 14. And there's the length of my radius. All right, we can do the same thing in number 2. Same thing in number 2, slightly smaller numbers. I want you to try number 2, so you can go ahead, pause the video, see what you get, and then we'll come back and check. So number 2, same thing. My C value, my hypotenuse is x plus 8, so that's my whole length there. So I'm going to have a squared plus b squared equals c squared, or x squared plus 12 squared equals x plus 8 squared. And I have to distribute this as x plus 8 times x plus 8. I have to FOIL the right side. So I get x squared plus 144 on the left. When I FOIL, after I FOIL and I simplify, I'm going to get x squared plus 16x plus 64. Notice my x squareds end up canceling with each other. So I have 144 equals 16x plus 64. Or 16x equals 80. So x has to equal 5. Right? Very, very tempting to write x squared plus, excuse me, is very tempting to write x plus 8 squared equals x squared plus 8 squared. This is wrong. Do not fall into that temptation. Don't do it. You have to remember squaring is something times itself. It's not x squared plus 8 squared. It's x plus 8 times x plus 8. Okay? All right. Numbers 3 and 4, these next two examples, are utilizing the fact that if you have tangent lines, you have right angles. And so, yes, that creates right triangles, but it also can create other shapes like quadrilaterals. And we can think back to everything we know about quadrilaterals and how those are connected to each other. So if I look at example 3, if both of these lines here and here are tangent lines, then that makes this a 90-degree angle and this a 90-degree angle. And in my quadrilateral, I now know 3 of my 4 angles. And in a quadrilateral, all my angles have to add not to 180 like they do in triangles, but rather 360 degrees. So I can figure out my x value by saying, okay, well, 90 plus 117 plus 90 plus x, all 4 angles have to equal 360. So then my x value, after I do my arithmetic, is 63 degrees. All right, so that's utilizing that theorem 12.1. If you have a tangent line, you have a right angle. Same thing's happening in number 4. We have a tangent line, so we have a right angle. You can solve for x. This time it's not a quadrilateral, but it's back to being a triangle. But our triangle here, we know what triangles have to add up to be. So we could add 90 plus 38 plus x. This time equals 180 because triangles, angles add to 180. I know it's been a couple months since we've really done anything with that, but we can't let that get, lost from us. And you get x equals 52 degrees. That leads us into our third theorem, which we are also going to add to our theorem page. So if you have that theorem page, pull that out. Otherwise, you can open up the one that you're creating yourself. I'm going to reopen this one more time so you can see where the theorem 3 is, 12.3. So our theorem is if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent to each other. So I'm going to draw an example on my note page. You can add this to the notes and to your theorem page if you want, but I'm going to focus back in on here. So this is saying, okay, I have a tangent line here, okay, and then let's say I have a tangent line here, and they intersect with each other outside my circle. So I've got a tangent line, so I've got a point of tangency, say here. I have a point of tangency there, and then they intersect at this point out there. This theorem is saying that this length from A to C is congruent to that length from B to C. So I can say my segments are congruent, or I can say the distance AC is equal to the distance BC. This is going to show up quite often when you have a circle inscribed inside of some sort of shape. And we'll see an example of that in just a minute. All right. But we have this example down here. AB and AC. Those are going to be congruent because they tell me that they are tangent. If the value for AB in example 5 is 25, so let's say this is 25, and AC is 6x minus 8, can you solve for x? So because they're congruent, I know I can set up an equation. I can say 6x minus 8 has to equal 25. So 6x has to equal 33. So x equals 5.5. Okay, that's example 5. Example 6 is a little different. Same picture, but this time I know AB is now 15, so I'm going to change the value there. And AC is now x squared minus 2x. So I can set up that equation, x squared minus 2x equals 15. We have a quadratic, and we just spent a long time practicing solving our quadratic. So the first thing we need to do in order to solve our quadratic is we need to set this equal to 0. So I'm going to subtract 15. Subtract 15. I get x squared minus 2x minus 15 equals 0. You can do quadratic formula. So x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Or you can factor. I'm going to factor. So to factor, I need my multiply number. I need my add number. I'm going to multiply, get negative 15, add negative 2. So I'm going to choose negative 5 and positive 3. So I'm going to build my box. I'm going to make those nice and straight lines, because otherwise it's going to bother me. I have x squared negative 15. I'm going to add in my two new chosen numbers, so negative 5x, positive 3x. So I can factor out a negative 5, an x, and a 3. So I now have, and I know I went through that pretty quickly. You can pause, slow down the video if you want. I have this right here. Now I can use my zero product property. That says x minus 5 equals 0. X plus 3 equals 0. So x could equal 5, or x could equal negative 3. I need to go back and check and make sure that these numbers make sense. I need to do that. All right, because I have two answers. They could both work, or one could work and one could not. So I need to go back and check. And so what I want to do is I want to plug them back in here to that AC value and say, okay, what is AC equal when x is equal to 5? Does that number, does the value I get make sense? So we're going to check this. If x is equal to 5, then I'm going to have 5 squared minus 2 times 5, or 25 minus 10, which equals 15. That works. So x equals 5, that works. X equals negative 3 could work as well. We're going to test that. If x equals negative 3, what does AC equal? AC is going to equal negative 3 in parentheses squared minus 2 times negative 3. Negative 3 in parentheses squared is positive 9. Minus 2 times negative 3, that is plus 6. That also gives me 15. That works. So that also is an answer. Both of these are correct. You need to give me both. There's no extraneous solution in example 6. Okay, so those are both correct answers there. Now, this right here, 7 and 8, we're not going to do them both. They are going to be filled out and posted on Schoology, so you can look at them later. These are utilizing this idea, but in a full polygon setting surrounding a circle. So if you see number 7, this is a triangle circumscribing the circle. Or we can say the circle is inscribed in the triangle. But what that's doing is essentially just creates lots of tangent segments. Down below we have a pentagon doing the same thing. So we're actually going to do number 8. Number 8, essentially we have all of these are tangent points. So Z, X, V, T, and R, those are all points of tangency. So we're creating all of these tangent segments that are coming off the edges. And theorem 12.3 tells me that these two are going to be equal. It also tells me that these two are going to be equal. And that these two are going to be equal. And these two are going to be equal. And I'm running out of space. And then our last one, I'm just going to point. This one is equal to that one. Because I can't fit 5 on there. So then when they say, okay, well, QZ is 9. If QZ is 9, then that's going to say QR is also 9. And if YX is 7, then that's telling me ZY also 7. And if XW is 12, that's telling me, well, VW also 12. And then, UW, this one's a little trickier. UW is the whole thing. That's 15. If VW was 12, that means UV has to equal 3. And then that's saying TU has to equal 3. And then our last one says, okay, well, if SU is 16 and TU was 3, that means ST is 13. That means RS is 13. So I can find the perimeter of my pentagon because now I know all of these individual segments. So now I can say, all right, well, that means there's my 9 there. Here's a 7 here. 12, 12, 3, 3, 13, 13. I can add them all up now. So I have 9 plus 9 plus 7 plus 7 plus 12 plus 12 plus 3 plus 3 plus 13 plus 13 all together gives me, I can do this, 88 as my perimeter. All right, so that's it for this section. When we come back, we're going to move on to chapter 12.2, section 2, where we talk about chords and arcs, and we'll fill in more on that theorem page. So remember, you want to be doing the examples. The examples are very helpful, but then that theorem page, when you do our quizzes and final exam, you can utilize this. This is going to be a condensed version. So you can add more to this. You can add some examples to it, but you want to keep it pretty condensed so that it's easy to find your theorems and your pictures and all of those other information.